Welcome to Toddcast number 63. It is the last of them for the semester, so your 310 experience is coming to a close. I just want to make note, everything I'm covering in the videos, except for some of the bio stuff from a little bit earlier, fair game. So we'll go over in class what exactly is fair game, but just note that everything will reach by the last day fair game, and that's going to be including the Baeyer-Villiger. So the Baeyer-Villiger reaction we actually looked at as a way to break open a ring system. So it's inserts an oxygen into a carbon-carbon bond where one of the carbons is a carbonyl. So you'll know it inserts an O. If it happens to be a cyclic structure, then you can hydrolyze the ester and break the ring open. So we learned you can break a ring through ozonolysis. If you make an alkene, you can break a ring if you make it a lactone, a cyclic ester, for hydrolysis. And the Baeyer-Villiger reaction helps us to turn a ketone into a lactone, or generically speaking, an ester. Okay, important reaction in that sense. So I'm not going to overemphasize the mechanism, but things are important in the mechanism that you note that the O will insert into a more crowded bond most of the time. Exceptions to the rule are going to be hydrogen, which for whatever reason migrates very readily, and phenyl groups, which can stabilize through resonance. But other than that, it's generally going to be the tertiary migrates preferentially over secondary, secondary over primary, and then primary over methyl. So as you learned when we did alkene chemistry, peroxy acids, that's what this is, such as MCPBA. Let me revisit what MCPBA is real quickly. Here's the B part, benzoic acid, but it's peroxybenzoic acid. So it's not just an OH, but an OOH. And then metachloro, MC, stands for meta, which is the positioning of these 1,3 on a benzene. Metachloro, peroxybenzoic acid. Okay, so we have that species. That has a tendency, as we learned, to deliver an O into your double bonds, or pi bonds. So when it's carbon-carbon double bond, we form an epoxide. That's going to be what happens here as well. So I'm just going to draw a cheat form of this, where I have this structure, I have the one bond O, and then I have my inserted O, which I'll put in blue. That's when it's going to come from the oxidation. Highly unstable, three-member rings are unstable to begin with. If you make a peroxide version of a three-member ring, it's going to be crazy. End up getting one R migrating over, and in doing so, going to take this bond and move it back. So we did that mechanism real briefly once upon a time, in maybe 3 or 4 podcasts ago. So I'm not going to overemphasize it, but just note that it happened. So in this case, we have a peroxy acid, we have our ketone. The two sides are equal by symmetry, so it doesn't matter if it slips in on the right side or the left side, it'd be the same compound. So an O can insert into this bond. This is known as a lactone. A lactone is a fancy way of saying a cyclic ester. And ooh, it's ester. There's 2 O's. They're also known as ester eggs to some people. So the mechanism can be a little cleaner here, hopefully. But again, that peroxy acid is going to insert into that. So my original, in this case, ketone, but I could have an aldehyde as well, but it's sort of the original ketone, I'm going to protonate it, make it reactive, so that now this peroxide oxygen is free to attack. Put the bond up there. When that happens, you have an OH, but you also have an unstable oxygen system here. So you will end up deprotonating. And you've now added across this carbonyl, so very much like your typical formation of a hemiacetal, only now we've added it with peroxy, hemiketal in this case, because it's hemi because of the OH, but protonate, break, make, deprotonate, That same mechanism always happens. And then we have this bizarre sort of O kicking in, R migrating over, and this moving across to that. So you end up with a deprotonated benzoic acid, or what used to be peroxy acid is now just a carboxylic acid. It has one less O, and you migrated the R across. And you end up transferring a proton. Everybody's happy in this. Okay, so the remember ring I showed you, that is, I guess, depending on your solvent, your conditions, one type of mechanism. This is going to be the mechanism I expect to be able to know and generate, because it is protonate, break, make, deprotonate. The other insertion mechanism, fair game in certain solvents. Okay, so here are my final products then. I have the carboxylic acid side product that came from peroxy acid, but we also have this new ester that forms. Again, if these R's are equal, it doesn't matter. But if they are not equal, then we have to worry about it. So in this case, what I have is, I have this reagent here where I have a secondary carbon and a primary carbon. And I should say more so, it's a methyl group. Notice the O inserted into this side. So we have secondary beating methyl. We also have, in this case, an aldehyde. Aldehyde actually beats, the hydrogen beats the secondary. I do one with a methyl and a benzene ring, acetophenone. The acetophenone beats the methyl. Or I should say the phenyl in acetophenone beats the methyl. And then finally, in this case, I have a quaternary and I have a secondary. So it's in more substituted size, quaternary wins. So really a tertiary migrating group compared to a primary migrating group. But the big picture of how this whole thing comes together then, H is the best at migrating. You're gonna get an aldehyde if possible. But after that, it's secondary over, or tertiary over secondary over primary over methyl. And then phenyl comes in roughly equal to secondary. Okay, so we have that. So just wanted to have a couple book problems up here. There's some particularly good book problems. So if we look at the two sides in the first one, we have this carbon with just a methyl, this carbon with a ring. You can see the O insert there. If we have an R group and an H, the O inserts at the H. And if we have these two sides, the O is going to insert into the more substituted side. So it's just a matter of knowing this relationship. And yes, I expect you to know that come test time. That's a better box. Okay, so it is worth it for you to go ahead and draw what exactly these products are. So let's go to this question mark and show that it is that compound. This next one's going to be probably the easiest to draw, in that, oops, I messed up the easy one to draw, apparently. This part stays the same, it just becomes an OH. And then the last one, the 5-membered ring becomes a 6-membered ring. And you have a carbonyl here, with those two groups here and one here. Which basically means you have that compound right there, is what we get from that one. Just a matter of figuring out where things go. So mechanistically, know the mechanism from the previous page. Know the acid catalyzed mechanism. And then know how to predict what your major product is. And know that that is a way to take a cyclic system and turn it into a lactone from a ketone, and then cleave it. That's the way to bust open a cyclic system. So it'll be helpful for synthesis. The last one I want to add, mentioned carbon nucleophiles in a previous podcast. Just want to make sure I cover this one. And once we do that, we are going to be complete on this chapter. So CN, excellent nucleophile, one of our big three. So thiols, CN, and amines are the ones that I hope you remember as being great nucleophiles. It can come in and attack the carbonyl. So when it does, it'll form a new carbon-carbon bond. And O up top, that O minus can pick up a proton from something, most likely HCN, because that's your most acidic compound. And you end up with this compound. Point of interest, acidic water conditions. You can cleave this, and you can end up with an O and OH, and then 3 H's on the other side. So remember, you can cleave cyano groups, C triple bond ends, and turn them into carboxylic acids and ammonia on the opposite side. You can also, let me get rid of that. You can also carry out other reactions on them, such as reduction. It is not an aldehyde or a ketone, so I need something strong like lithium aluminum hydride. Notice I can do this in water as opposed to having workup of a mild acid. So it works out pretty nicely this way, but I can add H's across this. So when I do, I'm going to treat this kind of like a carbonyl. When H minus attacks, breaks one, protonates from the water. Another H minus comes in, breaks the second pi bond, is protonated from water. So these H's here, the ones that end up here, these H's from lithium hydride end up being the ones there. Hopefully this seems nice and straightforward. Not a lot to this, just more reactions to add to your arsenal. Make sure you're making lists and charts or tables or whatever way you like to record reactions. But this semester you had a ton of different reactions. They're all fair game on the final. However, this last couple chapters, tail end of 12 and 19, with the crux of everything. And there are so many things we can do in terms of synthesis that you got to be ready for it. Okay. So, as mentioned, you can hydrolyze the cyano group, and you can reduce the cyano group down to an amine. So not much else to add to it. So cyanohydrins, OH with a cyano group on it, are a good intermediate to generate a carboxylic acid next to an alcohol. This could prove very synthetically useful at some point. Well, that's it. The semester is a wrap. So 63 podcasts. I know there's a reasonable probability, being these are on YouTube, that you, person watching this right now, may have no idea about what this class was, and hopefully you got some use out of them. But this message specifically to my class, you guys were awesome. It was so wonderful to be back in the classroom doing OChem, and I couldn't have had just a better group to share it with. So thank you a ton, and go nail the final. You guys are awesome. So signing off for the last podcast for the semester. Have an absolutely wonderful final, and thanks again. So see you soon. Bye.